Hi everyone! This video looks at a strong acid titrated with a strong base, and will focus on the pH calculation at the equivalence point. If the titrant volume in the problem is more than 0 milliliters, then we have to set up a millimole table. The E row of our millimole table tells us where we are on the titration curve and guides us as to how to proceed with the pH calculation. In this generic millimole table, we are only looking at the E row. What we see here is that both H plus and OH minus are consumed. They have reacted stoichiometrically and neither one is in excess. Because they both go to 0, this puts the reaction progress at region 3 of the titration curve, which is the equivalence point. Notice here that the only thing in solution is pure water. This means our pH value will be equal to the pH of water. Typically, you can just remember the situation and don't need to actually do the calculation, but here's why it works. We know that in pure water, the concentration of H plus that dissociates is related to the autoionization constant of water, or Kw. At 25 degrees Celsius, Kw equals 1.0 times 10 to the negative 14 out to 2 sig figs. The mass action expression shows us that the molarity of H plus times the molarity of OH minus equals 1.0 times 10 to the negative 14. This means that both H plus and OH minus are at 1.0 times 10 to the negative 7 molar in pure water. If we take the negative log of this value, we then get a pH of 7.00. So let's work through an example to see what this looks like when we are actually doing the calculations. So because we notice that our titrant is greater than 0 mils, we need to set up a millimole table. So we'll start by calculating the millimoles of our H plus. We get this from 10.00 milliliters of solution times the molarity of our HCl, which is equal to the molarity of our H plus. That's 0.04000 moles of H plus per liter of solution. Liters of solution will cancel, leaving the milli from the original volume. Looking at our sig figs, we have 4 sig figs from our volume, 4 sig figs in our molarity, and that will give us 4 sig figs for our millimoles. Doing the math, 10.00 times 0.04000 rounded to 4 sig figs will give us 0.4000 millimoles of H plus. For our hydroxide, we start with 12.80 milliliters of solution and multiply by our hydroxide molarity, 0.03125 moles of OH minus per liter of solution. Liters of solution will cancel. Taking a look at our sig figs, we have 4 sig figs in our volume, 4 in our molarity, and so this calculation will also be rounded to 4 sig figs. Doing the calculation, 12.80 times 0.03125 out to 4 sig figs gives us 0.4000 millimoles of hydroxide. We'll go ahead and set up our millimole table. So we have H plus plus OH minus goes to water. Set up our rows, ICE, initial, change, and end. Our units for this table will be in millimoles. And we'll draw a line through the water. Filling in our values, we have 0.4000 millimoles for hydrogen, 0.4000 millimoles for hydroxide. We subtract the lower number, but they're equal, so we'll be subtracting 0.4000 from each reactant, and that puts both hydrogen ion and hydroxide at 0 for our E row. Because both reactants go to 0, this tells us that we're at the equivalence point. And when we're at the equivalence point for a strong acid or a strong base titration, our pH equals 7.